Welcome to the deep dive. Today, our mission is to basically cut through all the noise and figure out how artificial intelligence actually learns from the information we feed it.
Yeah, it's a topic that's kind of misunderstood, honestly.
Completely. And we're exploring a really fascinating state-of-the-art paper from researchers at Peking University in Meituan. It's titled, How Should LLMs Consume High-Quality Data? Optimal Data Scheduling via Quality-Aware Functional Scaling Laws.
A bit of a mouthful of a title.
Oh, totally a mouthful. But, if you use AI tools to draft emails or write code or just answer random questions, understanding this gives you a huge shortcut. It explains why these models occasionally make these sudden, almost magical leaps in capability.
Right. And it's a fantastic piece of research because it challenges a very, very basic assumption that the tech industry has just sort of held on to for years.
Which is what exactly?
Well, we've spent so much time obsessing over gathering the perfect data, right? Like
Yeah.
cleaning it, curating it. But we've almost entirely neglected the biological rhythm, so to speak, of how a synthetic brain actually digests that data.
Right. And to put that into perspective, normally when we think about training an elite system, let's say like an Olympic sprinter, we obsess over the fuel.
Oh, absolutely. The diet is everything.
Right. The exact calories, the protein macros, getting the absolute highest quality food into the engine. But if you talk to a world-class sports scientist, they'll tell you the food itself is really only half the battle.
Timing is the other half.
Exactly. If you feed an Olympic sprinter their absolute best, most nutrient-dense meal exactly 3 minutes before the starting gun,
They're going to throw up on the track.
they're going to throw up. The quality of the fuel just doesn't matter if the timing and the delivery system are, fundamentally wrong.
Yeah, the physiological state of the system receiving the input matters just as much as the input itself. And that's exactly what's happening with AI right now.
Which brings us to this massive kind of hidden tension in AI development. The industry is sitting on mountains of pristine data. We're talking expert curated code, complex math proofs, entire textbooks,
The good stuff.
the really good stuff. But we might actually be feeding this data to these artificial brains completely wrong. We might be stunting their potential simply because we're handing them the best food right before the starting gun.
So to understand how we fix this, we really need to look at how these models are built today, which is a process called multi-stage training.
Okay, let's break that down for everyone listening.
Sure. So almost all large language models are built in phases. Phase one is pre-training, and this is really the brute force phase. Engineers basically back up a dump truck filled with a massive, messy, noisy scrape of the entire internet and just, pour it into the model.
It's the Wild West of data.
It really is. The AI is learning basic grammar, general facts, but it's also ingesting a lot of garbage. Typos, contradictions, weird internet forums.
Right, but then comes phase two, which is mid-training. And this is where you, bring out the fine china.
Yeah,
You take a much smaller, highly curated fraction of pristine data, perfectly formatted Python code, advanced calculus, flawless logic puzzles, and you feed this to the model to sharpen its high-level reasoning.
and intuitively, this multi-stage approach makes a lot of sense. It aligns perfectly with a well-known concept called curriculum learning.
Like in schools.
Exactly like in schools. In human terms, you do not teach a toddler multivariable calculus. You wait until they have the foundational capacity, the basic algebra, the geometry, before you introduce those incredibly complex concepts.
Right.
So saving the best, most complex data for late in the training process seems like just the smartest move.
Okay, let's unpack this, because this is the exact moment the researchers throw a massive wrench into the gears.
They really do.
They cite findings by Luo et al., pointing out this glaring, almost embarrassing conflict in this standard curriculum approach. In standard AI training, as you get closer to the end of a run, engineers do something called decaying the learning rate.
Right. They use schedules with names like cosine decay or warm-up stable decay.
So to clarify for you listening, decaying the learning rate basically means telling the model to calm down.
That's a good way to put it.
Early in training, the model is making massive, aggressive rewires to its internal rules with every new piece of information. But as it nears the end of training, engineers slowly dial down that intensity. They essentially tell the model, hey, you are almost finished baking. Stop making huge changes. Just make tiny, gentle refinements.
Right. But think about what that means when you combine it with the data schedule.
It's like saving the absolute hardest, most eliminating textbook for the night before your college final, but popping a NyQuil right before you open the book.
Yes, that is exactly what it's like.
I actually tried that method my sophomore year, and I can confirm my personal learning rate was effectively zero.
I think we've all been there.
Yeah.
But yeah, what's fascinating here is that we are handing the AI its most valuable, complex data at the exact moment its ability to absorb and rewire itself is artificially dialed down to a whisper.
It makes no sense.
None. And it completely shatters the illusion that data curation and training dynamics can be treated as two, like, isolated engineering departments.
Right, you can't have the data team delivering pure gold for the final phase while the optimization team is literally powering down the model's receptiveness for that exact same phase.
Exactly. This paper proves mathematically that data scheduling, which is what you feed it, and training dynamics, which is how vigorously it learns, are inextricably linked. You have to optimize them together.
And optimizing them wasn't just a matter of, running a few guesses on a server. The researchers had to mathematically rewrite the rules of how models learn.
They developed what they call the quality-aware functional scaling law.
Right. And they solved this massive joint optimization problem to figure out exactly how the quality of the data interacts with the intensity of the learning over time.
And out of all that math, they discovered that an AI model actually operates in two very distinct learning regimes. There's the noise-limited regime and the signal-limited regime.
Okay, here's where it gets really interesting, because to understand these regimes, we really have to talk about batch size.
Right, batch size is crucial.
For you listening, think of batch size like a stack of flashcards. It dictates how many examples the AI looks at before it pauses and updates its internal brain.
Yep.
So if the batch size is 4,000, it reads 4,000 flashcards, summarizes what it learned from the whole pile, and then makes one update. Now, my immediate assumption, and I think the assumption most people would make, is that looking at more data at once gives you a more accurate picture. Like, a bigger batch size seems inherently better.
And that intuition holds up, but only in certain situations. Specifically in that first regime, the noise-limited regime.
The dump truck phase.
Exactly, the dump truck phase. During pre-training, the model is drowning in noisy, messy web data. If you use a small batch size there, let's say you update the brain after every 10 flashcards, the model's going to overreact to garbage.
Oh, right. Because if a few of those 10 flashcards have typos or bad logic, the model updates its core rules based on errors.
Exactly. It amplifies the noise. So in the messy phase, you strictly need a large batch size. You need it to read thousands of flashcards at once, so the typos just kind of wash out in the average, allowing the model to find the true underlying signal.
The sheer volume protects you from the bad apples.
Right.
But what happens when we transition to the mid-training phase? Suddenly, we're dealing with the fine china. There is almost zero noise. The data is like a textbook perfect math proof.
And this changes the physics of the system entirely. In a low-noise environment, high-quality data can act as a signal amplifier.
Because you suddenly trust every single flashcard.
Exactly. You no longer need the protection of a massive batch size. You can drastically shrink it. Instead of waiting to read 4,000 flawless flashcards to make one update, you can read 500, update your brain, read another 500, update your brain.
And let's connect the dots here on why that actually matters mathematically.
Yeah, let's see that.
If you read 10,000 flashcards in batches of 10,000, you only update your brain once. But if you read them in batches of 500, you update your brain 20 times.
Exactly.
So by shrinking the batch size, you are forcing the model to make far more frequent aggressive updates. You are effectively jacking up the learning rate without risking the amplification of bad data.
That is the perfect way to look at it. You increase the learning intensity because you finally trust the teacher.
Right.
But there's still that second regime they discovered.
Yeah.
The signal-limited regime.
When does that happen?
This happens at the very tail end of training. The model has already extracted all the obvious patterns. And now, learning the incredibly deep, complex stuff becomes very, very difficult. The bottleneck isn't noise anymore. It's the sheer difficulty of acquiring that complex signal.
So what's the move there? Do you shrink the batch size even more?
Actually, no. In this late stage, clean data takes on a totally new role as a noise suppressor. You actually want to ramp the batch size back up at the very end.
Oh, interesting.
Yeah, by increasing the batch size, you reduce the frequency of the updates. And that quiets down any accumulated friction or terminal noise in the system, letting the deep patterns just settle into place.
It's a physical rhythm.
Exactly.
Early on with clean data, you drop the batch size to aggressively amplify signal. Later, you grow the batch size to gently suppress noise, which, I mean, that takes us out of theoretical physics and directly into the practical engineering recipe the researchers proposed.
The DSR recipe.
Right, drop-stable-ramp-up.
It is an incredibly elegant three-phase pipeline for mid-training. Phase 1 is the drop. The very second the model finishes its messy pre-training and transitions to the pristine mid-training data, you drastically cut the batch size.
You don't ease into it.
No, you drop it like a rock.
And then phase 2 is stable. You hold that batch size at that really low level for a sustained period. The model is rapidly churning through small batches, absorbing a massive amount of high-quality signal through frequent updates.
Yep. And finally, phase 3 is ramp up. At the very end of the mid-training run, you linearly grow the batch size back to its original massive size.
Which cools the system down.
Exactly. As we established, increasing the batch size has the mathematical effect of decaying the learning rate. You cool the system down, suppress the final noise, and lock in the intelligence. Drop, stable, ramp up.
Okay, wait, I need to play devil's advocate and push back on this for a second.
So go for it.
If shrinking the batch size gives us more signal, better updates, and effectively a higher learning rate, why are we holding this trick back for phase 2? Why not just shrink the batch size on the whole internet scrape from day 1? We could build a super genius model in half the time and save a fortune on compute costs.
It's a completely logical question. And if we connect this to the bigger picture, the researchers actually ran an ablation study to test that exact idea.
Oh, they did?
Yeah. They took the noisy pre-training data and applied the sudden batch size drop to it.
And let me guess, the model threw up on the track.
Spectacularly. I mean, it was bad.
Yeah.
They evaluate these models on a scale of 0 to 100 across various benchmarks. When they dropped the batch size on noisy data, the model scored a 33.24.
Ouch.
It was a disaster. For context, when they used a standard conservative schedule on that exact same noisy data, it scored higher, a 33.79. The old method won.
Right, because dropping the batch size removed the protective shield. It forced the model to make frequent, aggressive updates based on internet garbage.
Precisely. The smaller batch size just amplified the noise. However, when they applied that exact same drop strategy to the high-quality mid-training corpus, the trend entirely reversed.
The fine china phase.
Right. In that phase, the drop strategy shot up to a 49.07, beating the standard baseline by well over a full point.
Wow.
So the critical takeaway is that the drop only works when transitioning to a high-quality corpus. Clean data is the strict, non-negotiable prerequisite for the batch size drop to function as a signal amplifier instead of a noise amplifier.
Okay, so the theory's beautiful, the localized tests make sense, but we've all seen, theories fall apart when they hit industrial scale. They needed to prove this worked on a massive real-world model.
Oh, and they absolutely did. They tested the DSR recipe on a 15 billion parameter mixture of extras model, or MOE.
And for our listeners, think of a MOE model not as one giant unified brain, but as a massive team of highly specialized mini-brains.
Exactly. Even though the system has 15 billion parameters total, only about 2.4 billion of them are actually active for any given problem.
So it routes the math problem to the math experts and the poetry problem to the poetry experts.
Right. It's incredibly efficient. And they trained this MOE model across 108 billion tokens.
That's massive.
A token is essentially a word or a piece of a word. So we are talking about a model reading the equivalent of millions of entire books. This was a serious, computationally expensive training run.
Well, let's talk about the results because they are just staggering. They compared their DSR schedule against the industry heavyweights cosine decay and WSD, which is warm-up stable decay.
Right.
To give you context on the scale here, standard schedules were scoring around a 48 or 49 out of 100 on average across 14 different benchmarks. Cosine decay hit 48.48, WSD hit 49.76, but Drop-Stable-Rampup shattered the ceiling, hitting an overall average of 51.46.
Yeah, in the world of large language models where engineers fight tooth and nail for fractions of a percentage point, jumping a full 2 or 3 points is just explosive.
And when you look under the hood at where those gains came from, it completely validates the entire theory. The massive leaps happened in tasks requiring deep logic and compositional reasoning. Exactly. On the GSM-8K benchmark, which tests grade school math reasoning, DSR jumped by over 4 points. On the advanced math benchmark, it gained nearly 3 points. On Human Evol plus SRO, which tests complex algorithmic Python coding, it gained almost 2.5 points. It's like the model suddenly woke up and realized it knew how to do multivariable logic.
It's incredible. But, the researchers didn't stop at proving the recipe worked. They wanted to find the Goldilocks zone.
Oh, right.
They asked exactly how long should that middle phase be, the stable phase where the batch size is kept low.
So they swept the stable phase ratio from 0%, meaning they skipped the stable phase entirely, all the way up to keeping it low for 62% of the entire mid-training budget.
And the results formed this perfect, beautiful U-shaped curve.
Of course they did.
If the stable phase was too short, the model simply didn't have enough time to accumulate the complex signal. But if it was too long, the model ran out of time for the final ramp-up phase to suppress the noise.
So what was the sweet spot?
The absolute optimal sweet spot, the peak of that curve, was exactly at 24.9%. Keep the batch size low for roughly a quarter of your mid-training data budget, then start ramping it back up.
That's so precise. But okay, I noticed a really weird contradiction in their benchmark data, and we have to unpack it.
Oh, I think I know what you're going to bring up.
When they looked at MMLU, which tests general English knowledge across subjects like history and law, the model actually preferred a slightly longer stable phase. But when they looked at CMMLU, the exact same kind of test, but in Chinese, it preferred a shorter stable phase.
Yeah, the translation dynamics alone alter how the model absorbs the data.
But it gets even more confusing with the coding tests. We just talked about how algorithmic coding tasks like Human Evil Plus thrived under DSR. But there is another coding benchmark they tested called Big Code Bench. On Big Code Bench, DSR actually underperformed the old baseline. The model got worse. How can this brilliantly optimized schedule be a massive success for one Python coding task and an absolute failure for another?
That paradox is arguably the most important discovery in the entire paper. This raises an important question, and the researchers address it by introducing a concept called the early phase gap.
The early phase gap.
Yes, it highlights the reality of heterogeneous training dynamics, meaning not all types of intelligence are built the exact same way.
So walk us through the mechanism of that. Why does one fail while the other succeeds?
Let's look at what is physically happening inside the model during that low batch stable phase. Because the batch size is small, the model is making frequent updates based on smaller slices of data. Inherently, that introduces a little bit of friction or, noise into the rewiring process.
Right.
When the researchers mapped out the training trajectories, they noticed something wild. For tasks requiring deep, multi-step compositional reasoning, like the math equations or the complex algorithms in Human Evil, plus the model's performance during the stable phase actually dipped.
Wait, really? It looked like it was failing.
It looked exactly like it was failing, but it was actually doing the hard work beneath the surface.
It was accumulating a massive amount of latent signal.
Exactly. Human Evil Plus requires the AI to figure out how to build a complex sorting array. It's logic. If the AI gets a little noisy during training, it's okay because it's feeling out the logical pathway. It tolerates the temporary noise because it's building deep structural connections.
Oh, I see.
And the moment the schedule transitions to the final ramp-up phase and suppresses that noise, the performance on those reasoning tasks just explodes upward.
So they're basically digging the foundation of the skyscraper. It looks like a messy hole in the ground until the building suddenly shoots up into the skyline.
That's a great analogy. But now let's look at tasks that rely on pure factual recall or highly specific API knowledge, like Big Code Bench.
Okay.
Big Code Bench isn't asking the model to solve a logic puzzle. It's asking the model, hey, what is the exact name of the specific function to call the Twitter API?
Oh, so it's pure memorization.
Yes.
Oh.
And these tasks are incredibly sensitive to noise. If the training is noisy during that low batch phase, the AI might accidentally remember get Twitter data instead of the actual factual syntax, which is fetch Twitter EP252.
Right.
The noise scrambles the fragile factual connections. That scrambling is the early phase gap.
It permanently damages the model's ability to recall precise facts.
Precisely. If a task is heavily noise sensitive, forcing the model to spend 25% of its time in a low batch, slightly noisy state is going to corrupt those specific memories. And the final ramp-up phase just won't be long enough to recover the lost ground.
That is genuinely profound. I mean, it means that deep mathematical reasoning and encyclopedic factual recall have fundamentally contradictory needs when it comes to how they consume data.
Exactly.
Math wants you to drop the batch size, increase the update frequency, and grind through the logical patterns, even if it gets a little chaotic. Factual recall wants you to keep the batch size huge and stable so you never accidentally scramble a date, a historical fact, or a specific line of syntax.
It moves the entire industry past the simplistic idea that better data magically equals a better model.
Right.
The researchers proved that high-quality data is not merely an ingredient you toss into the blender. It is a variable that must physically dictate how your computing power is allocated. You have to change the rhythm of the GPUs to match the quality and the purpose of the data flowing through them.
So to bring this all home for you listening, the next time you log into Claude or ChatGPT, and you notice it has suddenly made a massive leap in its ability to write a complex script, or it suddenly solves a math problem that it couldn't handle last week, remember this deep dive?
Yeah.
It is not just because the developer scraped a million more math textbooks and dumped them into its brain. It is because brilliant engineers discovered the exact rhythm, the precise choreography of scheduling and batch sizing to finally unlock the value of the textbooks that were already in there.
We finally stopped giving the athlete a sleeping pill before the race.
Exactly. They align the physiology of the learning process with the nutrition of the data.
It's beautifully said.
But this leaves us with an incredibly provocative thought to ponder, entirely based on that contradiction we just uncovered.
Oh, what's that?
Well, the entire AI industry is in a dead sprint toward AGI, artificial general intelligence.
Right.
The holy grail is to build a single monolithic supermodel that is an absolute genius at everything all at once. We want a model that can do the deep compositional math of human evil plus cave and simultaneously possess the flawless encyclopedic API recall of Big Code Bench.
A master of logic and a master of memorization.
Right. But if those different tasks have completely fundamentally contradictory needs for their optimal data schedules, what happens when we try to train them together?
That's a million-dollar question.
Will the perfect rhythm that unlocks superhuman mathematical reasoning inevitably and permanently sabotage the model's ability to recall specific facts? Are we approaching a physical limit where being perfect at one type of thinking requires a model to be slightly deaf to another?
It's a huge hurdle.
It really is something to think about the next time someone promises you an AI that can do it all. Until next time, keep diving deep.